All right, so here's the thing. Stay with me now. Stay with me. At the end of the show, so they go through all this silly stuff, and they get they get somebody who won the most money, and they say, okay, we're going to let you give back that money and choose one of these 3 doors. Behind 2 of those doors is something that the person doesn't want. So normally it was a goat. And then one of my classes, they said, well, what if I want a goat? Well, then shit, I don't know what it is. It's an old bathtub. Sounds good to me. I'm like, all right, it's a pile of dirt. Yay! I'm like, screw it. But you're with me. And behind one door is a car, a trip to Paris, a boat, a suitcase full of money, $25,000, whatever. You guys understand what's going on? 2 doors suck and 1 door is awesome. Let's make a deal, exactly. Right? That's, Monty Hall was the old host of that. You guys kind of with me what's going on. And by the way, before I jump into this, anybody ever watched the show Mythbusters? It's now... All right. They did a whole episode on this, where they actually had people come in and choose a door, and they did it. People get so confused about this, and actually statisticians were up in arms about this. It was in Parade, Marilyn Vos-Savant. She's this person that's got a high IQ, and she kind of explained how this worked, and people said, no, it's wrong. And I'm like, it's so freaking simple. But it's not, it's counter to what we think. So here's how it happens. Pick a door. 1, 2, or 3? 2. 2. Okay. All right. I love it. So I got double verification. I only said 1 person, but okay. So you guys picked door number 2. I open door number 3 and show you that there's a goat. Let me draw my mutant goat. Oh God, why? Why? Mutant goat. Do the goats? Yeah, they do. Let me put goat. It is a goat. I told you it's a mutant goat. Leave the poor thing alone. It's had a rough life. All right. Now watch. You pick door number 2. From right there, what's the probability that he got the big prize?
50%.
No. So before I show you that, when he picked that door, what's the chances he picked the door with the prize? 1 door has the prize out of 3. That's the basic idea of probability. How many things match what you're looking for divided by the total number of things that could have happened. So 1 door out of 3. That's the probability that he picked the right door. Which means, what are the chances that one of the other 2 doors has the prize? 2 out of 3. 2 out of 3 that one of the other doors has the prize. So as the host, what do I know? I know where the frickin' prize is, right? So I'm going to open a door and ask him if he wants to switch doors. Would I open the door with the prize behind it?
Never.
If I did, the show's over. There's the prize. You got to go. See you. Oh, we got time to fill? Oh, shit. I did that wrong. I'm going to show him a goat. So here's the goat. I'm not going to draw the poor little dude, because you made fun of him. You left.
He's not mutant. He's special.
Sure. No, he's mutant. He's got powers. So I show you there's a goat here. Should you switch? Would switching increase your chances of winning or not? Or would it stay the same?
No, it's the same.
And see, that is wrong. Again, only 1/3 of the time he's going to pick the door with the prize. So 2/3 of the time he didn't pick it. So I show you there's a goat there. So there's actually a 2/3 chance that that door has the prize.
But what if I pick the right door already?
So the probability-
And that only happens how many times? 1 out of... Now listen, okay, stay with me. It's a beautiful question, Sharon. Come on, stay with me. Stay with me. That only happens how many of the time? 1/3 of the time you pick the right door. And then as the host, which door am I going to open? Either one. But what changes things is the host knows where the prize is. So 2/3 of the time, you don't pick the prize. And then which door am I going to open?
I don't like this game anymore.
Which door am I going to open? The one with the goat. So more often, the door that I didn't open has the prize. All right, now watch. Let me take it even further. No. You don't quite get it. Imagine 100 doors. No, go with it. Oh, you guys are like, screw that shit. Now, this is going to make it easier to understand. This is going to make it much more extreme. You pick door number
51.
2, sure. I don't want to draw through. All right. I open every other door to show a goat except for this door. Every other door has a goat. Goat, go, 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 go. So why didn't I open that door? More than likely because that door has the frickin' prize. So should I switch? Shit, yeah.
You know how many times I've seen people do that on way to make the other lady lose their car and they lose their place?
No, you're remembering the bad times more than the good.
Because she's a woman.
Say again?
Anyways.
How does this apply to what?
Are you saying in the first example there's like a way to tell that the right door is... Do we even know which one is the right door?
I really want to. Here's the thing. Guys.
Okay, so let's go back to the first problem. So he picks the goat. And then he says, let's make a deal. Do you want to switch your answer? Hell yeah, I want to switch my answer. Because the probability of me switching the answer and getting the right door is
Is
better.
twice as high as what you currently have.
But why would you basically tell me to switch?
He's not.
That's what you...
1/3 of the time you should not switch. 2/3 of the time you should.
Once he eliminated that other door, the probability got better for me.
Yes, the probability got better. So if you switch, will you win for sure? No, because that's freaking life. So probability never says this is almost never. In real life,
Probable,
never.
not guaranteed.
It's definitely going to happen. No. So if you have a 90% chance of something happening, the mistake humans make is, oh, cool, that's going to happen. And then it don't happen. You're like, probability is stupid. No, 90% chance means it's going to not happen sometimes. We see a high probability and our human brains say, oh, it's going to happen. 90% chance of rain. Oh, it's going to happen. It didn't rain. Stupid weather forecast, it wasn't matter.
But there was still that 10%.
Yes, there's a 10% chance it wasn't going to rain. Doesn't mean it's not going to rain. It just means it's more likely to rain. So here's a good example also. What if I look off in the distance and I see somebody walking to me? I can't quite tell. They're way far off. I can't tell if they're a man or a woman yet. They're way out there. What's the chances they're a man or a woman?
50-50.
All right.
1 out of 2.
Now, let's say that I looked and I saw them get off of a Harley-Davidson motorcycle.
In your mind, you're thinking man.
The probability it's a man just went up. Now, I love it when I say that, and some girl goes, I ride a Harley-Davidson. What do you say? I'm like, I didn't say shit about girls don't ride Harley-Davidsons. I said the probabilities increased that it was a man. It doesn't mean the probability of a girl went to 0. It just means it went down. Do you guys understand?
Yeah.
Our human brain wants to make everything black and white. It wants to make it 0 and 1. Probabilities are like, well, yeah, sometimes this is going to happen. Which is one reason why people don't trust statistics, because statistics just tells us it looks like this is going to happen. In fact, right now there's the election coming up. Hopefully everybody understands that's happening. You can't escape it. I'm sorry, right? South Park always makes me feel better about such things, but so you should watch that. But you always see these polls, they say 42% are going to vote for A and 44% are going to vote for B, but at the bottom you see plus or minus 4% or something, right? So actually it could be completely the other way. And that plus or minus 4% is statistics. We can actually calculate that. And there's never going to be a definite answer. Never. Because that's life. That's why I love statistics. Because statistics is the most honest math. It says, here's the answer, we think, give or take 3%. Because that's freaking life. Yes?
This morning, I can't remember, it was 5 o'clock this morning, I don't remember which news channel it's on, but they had a theory of probability map up, and they picked 2 states and said if Trump wins this state, then this is going to happen, but if Hillary gets this state, then this is going to happen. So that's basically statistics, instead of applying the point or
Yes.
plus
Yes.
something. Because if Hillary won that one state, then all kinds of other things were going to happen, but if Trump won the state, it was pretty much solidifying his chance of presidency.
That's because they got more than her.
So I think that I didn't get it when I was watching the map this morning. I was like,
What the hell are you talking about? But yeah, they're taking these steps. There's a certain chance this will happen. And then there's a certain chance if that happens, this will happen. And the further out they go, the less and less chance they are that it's right. Because all it takes is one branching off another direction and they're wrong. Sort of like, any of you guys watch college basketball at all? Some of you guys? You know that huge bracket, and they actually had that company that was going to give $1 million if you chose the bracket correctly? Well, the minute, there's so many branches in everything that the minute you're wrong once, you're out. And so the chances you get it right are like astronomically huge against you.
That's just like in Vegas, if you go to the sports book and you choose the large ticket with 10 teams, you're likely to lose that
Yes.
because there's more probability.
It's like the pick six at Del Mar, right? So the true gamblers are all like, yeah, huge returns. Someday it'll happen.
For Vegas, that's how we do it.
Oh, I got you. I got you.
Go hard or go home.
I ain't that way. I'm that way a little bit. I have a limit, and once I hit it, thank God I can get out. I'm not like a, hardcore gambler. Thank God, because my my true limit would be not very far, because I don't have a lot of money. So hey, all right. So the basic idea I want you to get from all this is probability is not hardwired in our brains. That's why we have to trust the mathematics behind it to tell us what the situation looks like. But again, as a human, we see stuff like there's a 99% chance of this happening, and we think that means, it's definitely going to happen. No, that's not what that means. It just means that's the most likely thing to happen. Something else could happen. Maybe. So I'm not saying that you're going to see problems like this that you have to write a paragraph explaining to me. The only thing I'm doing this for is to show you why we want to use math to help us figure out probabilities. Because it's not intuitive to us, humans. Alright. So to kind of build our way up to probability, we start with this. Probabilities are based on how many total things could happen. So for example, if I had a deck of cards, how many cards are there in a deck of cards? No jokers, just normal deck of cards. Anybody know? Do you guys, anybody play cards at all? Anybody? 52. I had an older sister, so I knew how many cards were in that deck, because I would suddenly play 52 card pickup. Jeff, 52 card pickup, pick them up. And I'm like, oh shit, just 52 cards, right? Unless one fell under the couch, and then nothing ever worked it right again. So, what's the probability I pick a certain card, the 7 of hearts? There's one 7 of hearts out of 52 cards. So that's why what we do is, when we study this, is we start with, are there ways to figure out how many total things could happen? Now with cards, I can just count the cards. And I don't mean counting the cards and winning at blackjack or something. I just mean there's 52 of them. I can count them. What about this situation? What if I, let's see. All right, let's go back to the horse racing. What if there was 2 races I wanted to bet on, and there's 7 horses in the first race, and there's 5 horses in the second race, and I'm going to bet on both races. I'm going to pick one horse to win in both. How many total tickets? So, for example, these 7 horses we got C Trisket. How do you spell Trisket? C Trisket, and you got Faux Chrome, and whatever. You got 7 names there, right? And then here you got 5 names. My creativity is low this morning. Too bad for me. I need some coffee. You guys with me? So one ticket could be C Trisket and A gonna happen, right? That probably is a horse's name somewhere. Have you ever seen horse names? That could be any damn thing. It's almost like boat names, just better. So one ticket could be C Trisket and ain't gonna happen, right? And so I need both of them to win for me to win. So how many tickets, how many total pairs of names could I create between these 2 races? Nope. Now think about this. If I choose C Trisket here, if I choose that guy here, C Trisket, just because I like the name, how many things could I choose after that? 5. So there's 5 choices after I pick that one. In fact, there's 5 choices after I pick any of these. Do you guys see that? So if I pick this one, I got 5 choices after that I can pick from. So there's 5 things I can make with him first. How many things can I make with him first? 5. And how many of these are there?
7.
That is the definition of what operation? Each one of these 7 things has 5 things after it. That's the definition of multiplication, right? There are 5 things for each of these 7 things. So how many total things are there? 35. This is what's called the fundamental counting principle. If there are m ways to do this thing, and n ways to do this thing, and so forth, you multiply m times n times whatever to get the total number of ways to do something. Just to show you a concrete example. Let me get away from horse racing in case that disturbs anybody. There's so many things you could not like about horse racing. So let's come to having babies. What kind of babies can you have?
Girl and a boy.
Girls and boys. I like it. I like it. So we're not going to get into any gender controversial crap. We're going to talk about girls and boys, right? Okay. So if a couple has 3 kids, they're going to have 3 kids. What could those kids be? They could have all girls, for example, right? I like it. They could have all girls. All right, let's do this really systematically. Or they could have one boy, right? They could have all girls, or one boy there, or one boy there,
Or all boys.
or 2 boys there. Let me stop there for a second. That's all the ways to have a girl first. Is that cool? I got to have a girl first, and then 2 girls, a girl first, and then girl boy, a girl first, boy girl, or a girl first, boy boy. There's no other ways to have a girl first and then something else happen after. Is that cool? So now I just do the whole thing again, except I have a boy first. So it'll be boy, 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 girl, 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 boy, boy, girl, boy, boy. I like it. So how many total possibilities did there end up being? 8, right? 4, 8. Now let's see why that makes sense. So this is a concrete thing. I can count them. I didn't want to come up with 7 horse names and 5 horse names and then write them all out. That would have been 35 long of a list. I don't want to do that. Okay. But watch this. So I have 1, 2, 3 babies to make. How many choices are there for the first baby? 2. And how many for the second baby?
2.
And how many for the third baby? 2 times 2 times 2 is? There we go. That's what that means. That's a fundamental count. Even without making the list, I could just multiply the choices to see how long the list would be. Does that? So for the horse race, 7 horses and 5 horses, I can make a list of 35 possible pairings of horses. That's how long the list would be of all the choices I have to make. And how many of those tickets will actually win? 1. Maybe. So, what about this? I want to make a password. And I need the first thing to be a letter. And the next 2 things to be numbers. How many total passwords could I make using this?
Well, there's 26 letters.
All right. So it's all about the total possible options I got. So I got 26 options for the first thing. Now this is where people kind of forget a number here. How many numbers, how many single-digit numbers are there?
10.
10 is right. Don't forget 0. Poor little 0 dude. Right. So one password could be A00. That could be a password. And of course, everything would say weak. You ever put password weak? I'm like, I'm not done typing yet. Still weak. Oh, screw you. You all weak. Yeah. So there's 10 numbers and then 10 numbers. So for every letter, I could pick 10 numbers. For every pair of those, I could pick 10 more numbers. So it's all about the total options you have. So how many total passwords that look like this could I make? 2,600 passwords. There's always more than you think there will be. Right? So the classic thing is if I have a pizza with 10 possible toppings. So I could choose no toppings, I could choose 1 topping, 2 toppings, 3 toppings, up to 10 toppings. You guys with me? There are millions of types of pizza you can make. You don't believe me, and I don't care. And the thing, it's the same thing as the birthday thing. When I said somebody has the same birthday, if I have enough people in the room, you guys think you don't realize how many different pairings I can make. How many different two-topping pizzas are there? Well, I can have pepperoni and this, or pepperoni and this, and pepperoni and this, and pepperoni and this. Or I can have this and this, or this and this, and this and this. Right there, just for two toppings. There's a ton of them. So imagine 3 toppings. Holy shit. Do you guys... So our brains are not hardwired to think the right way. So thank God we made some math to show us what the hell's going on. This is where the math exceeds our brain. Sometimes you guys don't like math because I figured that problem out without using any algebra. I'm like, again, if it's algebra class, you better use freaking algebra. But here's a really good example of you ain't gonna get the answer unless you use some ideas of math. Because our brains just don't work that way. Okay, what about this here? What if I said I want to make a license plate? Oh shit, how do you spell license plate?
Oh no.
A lot of numbers.
I want the first 3 to be letters, not repeats. So let's just say no repeats, Jeff. That makes more grammatical sense. And then I want the last 4 to be numbers. Again, no repeats. Oh shit. Oh, see? Now think about it. If I'm not letting you repeat a letter,
Oh,
how many choices do you have for the first letter? 26. So you pick a letter, right? But now how many choices do you have for the next letter? 25, because you're not allowed to repeat that same one. You got one less option now. Times 25, 24. Now numbers. 10, 9, 8, 7. Somebody help me out. Somebody got the calculator out?
yep, 7,862,000. Oh, I'm sorry, 78,624,000.
Like that?
Yep.
Okay, cool. Oh, probably more than you thought it would come out to be, right? This always happens. This always happens. And this is related to why the lottery odds are the way they are. Because of all the choices you can make. Anybody ever play the lottery? You can be honest. I've played it. I teach statistics and I say, if you're going to put money on a ticket, give it to me because I'm going to put it to better use. But every now and again, I'm like, yeah, what the hell? Here's $1. Give me a number. None of them matched. Yay, Jeff. Right? So it's, who cares? I always feel bad for those people that are spending. I'm like, you can buy bread with that. Don't do that. Don't do that, please. All right. But that's huge. It's way more than you might have thought was going to happen with this problem. Because our brains just can't process all the possible pairings. Our brains aren't hardwired to do that, so we don't trust it. But the math says, yeah, there it is. That's how many license plates you can make. Now, of course, is that the total number of license plates that would be allowed? You can imagine what words you can make here that they probably don't want on your license plate, right? So then you have to go from here, you have to decrease it, but you know, that's the idea. Maybe. Now, if I allowed repeats, that number would go even higher very quickly. Yes, sir.
Do we always know the total number? Like, we know the letters are 26.
Yeah, they have to tell you.
Oh, okay.
Yeah. So I could say I only want to use vowels here, and then I'd still have to tell you, well, are you considering Y to be a vowel? Because Y is one of those that can go both ways, which is nice for Y, right? It's got more options. Okay. By the way, just so you know, we're still in section 7.1. 7.1 is all about this fundamental counting principle. Stay with me now. So hopefully you understand I can make up any situation where there are options. So what's another situation in your life where you have multiple sets of options for a single kind of outcome? So what I'm thinking about is, let me see if anybody can come up. This happens all the time. Normally with like major purchases, don't you have all these options?
Cash or credit?
Lottery is a very straightforward one. You have numbers.
Cash or credit?
Okay, sure. I'm thinking about like when you buy a car. You have options, don't you? You have color options. Maybe some of you guys have only one color option. I don't know. It can never be anything except dark green. Or
You can model.
yes, exactly. What make, what model. new or used. If it's used, you got a whole buttload of options to go from there, right? Buttload is an actual amount, just to let you know. It actually is. Where was I at? And then you got the option of, if you're getting an SUV, do you want it to be all-wheel drive? Do you want it to be four-wheel drive? Do you not care? And each set of options would multiply, and that would tell you the total number of cars that you could make from all these options. But I have to tell you how many, and the minute you know how many options each thing has, you just multiply them all together. So you just have to figure out how many options does each choice have, multiply them together, and that's the total number of outputs you can get. So I can get a green Ford Fiesta with, I don't even know, it's going to all-wheel drive, and a moon roof. And look at it and go, what was I thinking? Let me try. I'm sorry if you've ever had a Ford Fiesta. Are they nice? I don't know. Yes? I'm sorry. Somebody's like, don't be dissing my Fiesta. Sorry. Blah, 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 blah. So this one, you really just have to get into this and try it. Let's see. So what about this? Here's a slightly different take on this. What if I had 8 paintings to choose from? I got these 8 paintings, and I want to put them up here, just because, or over there even. That's even better. This has got orange, and it's got the thing. It's got that poor wall has nothing, right? So let's say I'm going to put 5 paintings up on that wall, and there's 5 positions where I want to put paintings, and I have 8 total paintings. How many different arrangements of paintings can I put up there? So I got 5 spots, right? So I got 5 spots. 1, 2, 3, 4, 5 spots. Are you guys with me? So how many choices do I have for the first painting? 8. 7. Obviously, I can't go, well, I'm just going to stand here forever and do this. That painting is in both places. I'll just do it really fast, and it looks like they're in both places. No. So once I choose a painting, it's not there anymore, right? And of course so this guy has 6. So that's a little different from what we were doing a second ago, just a little bit different. Because I got one group and I'm distributing it amongst all these spots. But it works the exact same way. This fundamental counting principle is pretty strong. That's why we call it the fundamental counting principle. Cool, I like it. So if you multiply this out, it gives you all the total number of different arrangements possible for the paintings that you have. I like it. I like it. Now, that's number 1. What if there's a certain painting I wanted in the middle? So there's a certain painting I really like. It's a painting of...
Just one option.
There's my beautiful painting there, right? Alright, so there's one option there. So now help me out. What about for the rest of them? Good. 7, 6, 5, 4. So if there's a certain painting I want in the middle, it's going to really take the total number of options I have down, which only makes sense. At least that part of our brain goes, okay, that makes sense. What doesn't make sense to our brain is how big this number gets. Because our brain says there's only 8 paintings. Did anybody do this for me? Where are my people that are doing this for me? 30, 120, 840, 840, 67, something. Somebody help me out.
6,720.
Oh, good. I was right. I don't believe it.
So it is 7 times 6.
30, 120, 840.
Yep.
So if I say there's one painting that's got to go in a certain spot, the number of possible arrangements went way the hell down, and this number is probably way larger than any of you would have guessed. I say I have 8 paintings, I want to put 5 of them up there. There's no way anybody would have guessed there's over 6,000 ways to do that. And right now you guys are like, I don't trust that. But it's just, we got 8 paintings we could put there. And then I have 7 paintings that I could put there. I mean, that is the true thing. That is how many arrangements there are. And that's why the odds of winning the lottery are so astronomical, because I think on one you pick like out of 50-something numbers for I don't know how many spots. Obviously, I play it all the time. Anyway, I just let the computer give me something. All right. Whew. So you're going to get a little bit. Yeah.
If you're playing the lottery, are the odds better if you choose your own numbers or if you let the computer choose?
It depends on how much of a conspiracy theorist you are. You know, like the computer knows. So screw the computer. I'm going to pick my own. But in reality, it's the same thing. Yeah.
Can you eliminate the numbers that were used or that won to get a better?
Do you think that's the way they do it? Do they think they say, well, that number one, we're not going to use it again?
That's just, I already won, they've not been here no more.
So anybody who does, I've seen those things. They are people that don't know statistics, but they know that other people don't either, and they're trying to make money off of them. Of course they are. So people exploit other people's misinterpretations all the damn time. And that's one where they say, buy this little pamphlet, it'll tell you over the last 3 weeks was. Screw them. They don't know shit. If the number 17 won last week, the chances that it wins this week, like out of the whole thing, is the same as it was and the same as it will be. So that's another thing people have a misunderstanding about with probability. What's the probability? If I toss this and I get heads, and then I do it again, let's see if this will happen, or I'll have to lie. Oh, good, heads. Is the probability the next one's heads? Has it changed? I got 2 heads in a row just now.
So what?
What's the probability it's going to be heads again? Still the same as always. So there's no memory. This thing doesn't go, I remember. Oh shit, I better twist one more time. No, that would be freaky. Little dude talking to me, then I need my meds.